Welcome to the flock. Let's dive into the concept of molarity by solving questions like the one above my head. What is molarity? Well, molarity is the moles of a solute per the liters or volume of a solution. We represent that as literally a number of moles of solute divided by a number of liters of solution. And I've found that the best way you can visualize this is thinking about a smart water bottle. These smart water bottles are all typically 1 liter for this size. Well, then how much is a liter? A liter is 1,000 milliliters. What's a mole? A mole is 6.02 times 10 to the 23rd. That's a really big number. We're going to represent a mole with 1 red pom-pom. So if we have 1 red pom-pom in a 1,000 milliliter beaker, we now have 6.02 times 10 to the 23rd atoms or molecules, i.e. a mole, in the beaker. What if I add 9 more moles for a total of 10 moles in this beaker? Well, that's great and all, but to have molarity, I need more than just moles. I need a solution or a solvent, i.e. water. So now, if I take 10 moles and I add 1 liter, I now have a 10 molar solution. Or another way to say it would be 10 moles per 1 liter. So let's get back to solving that question. What is the molarity of 5 grams of sodium hydroxide in 750 milliliters of solution? If we think back to our molarity, we know that molarity is moles per liter. We have neither of those in the given values. Currently we have grams and we have milliliters. Neither of those units match what we need for moles per liter, i.e. molarity. So the first thing we have to do is convert our grams to moles using dimensional analysis or stoichiometry. As with any conversion, we have our magical line to freedom, a space for our answer. The goal is moles because we're trying to get from grams, the given, to moles so that we can actually plug it in and solve for molarity, which is the question. So we're going to put our given, the 5 grams, at the start of our line. Well, 5 grams of what? 5 grams of NaOH. And anytime we need to go from grams to moles, we're going to use molar mass. By looking at the periodic table and adding together the pieces of our compound, we can obtain the molar mass. Each sodium atom weighs 22.99, each oxygen atom weighs 16, and each hydrogen atom weighs 1.008. When we add those 3 values together, we get 39.99. So plugging in our molar mass dimensional analysis domino, we can now put 39.99 as our grams of NaOH per mole of NaOH. Here our units cancel, grams cancel. We are indeed left with moles for our final answer of NaOH, which is the chemical of interest. So now multiplying across the top and dividing the bottom, we just have 5 times 1 divided by 39.99 to give us a value of 0.125 moles of NaOH. Well, that's awesome. We finally have grams to moles now, so we can actually put that in the numerator of our molarity setup, i.e. moles per liter. So now to get the actual value, can't we just take our 750 mils and put it down here? No, of course not, because that's in units of milliliters. That's a big no-no, big red X. We're trying to get units of liters in order to plug this into our ratio, our moles per liter. So we need to take our 750 milliliters and convert that to liters first. In other words, remember that 1 liter is 1,000 milliliters. That means we have to move the decimal on 750 back 3 times because there's 3 zeros in 1,000. So moving the decimal back 1, 2, 3 gives us 0.750 liters as our denominator. So the correct setup should look like that, 0.125 moles over 0.750 liters. Notice that our units are in moles per liter. That is what we were aiming for, molarity. Now we can actually solve for the molarity because we only have to divide the 0.125 by 0.750, a simple math expression, to get our final answer, molarity. When I divide those 2 values, I get 0.16 moles per liter. Another way I can write this is 0.16 capital M. Capital M does not mean McDonald's in this case. It literally means mole over liter. So what's the purpose of molarity? It's a measure of concentration. It tells us how concentrated something is. For example, if you were comparing 18 molar 18M nitric acid to 1 molar M nitric acid, the larger value means that it's more concentrated. It has more solute per units of solvent. So 18 molar nitric acid is much more caustic, much more dangerous than 1 molar because of its concentration. Likewise, if you're comparing concentrations of less than 1, like 0.59 molar nitric acid compared to 0.1 molar, the 0.59 is a larger value, therefore more concentrated and more caustic than 0.1 molar in comparison. Let's do another practice example, just like the one we tried before. Go ahead and pause the video here to give this one a try yourself. Ready, go! Let's do this. Hopefully you got that as your final answer. There's just 3 different ways you can write it with those moles per liter or molarity units. But what if the question gave you a concentration, it gave you a molarity, a molar solution, and it's asking for moles? We're still going to use dimensional analysis as we always do. We're going to put our given as the first thing on the line. I like to start with givens that only have 1 unit associated with them. In other words, I would start with 25 milliliters as my given, the first thing on my line, as opposed to 5 molar, which would be 5 moles per 1 liter. That's kind of a complicated thing to start with on the first of your line because it has 2 units associated with it. Let's start with the 25 milliliters instead. Now, if I need to go from 25 milliliters to moles, I first need to get rid of the milliliters so that I can use molarity in liters to get to moles. So we already know that there are 1,000 milliliters in 1 liter. I can use that as that conversion factor. If you noticed before, I also used a conversion factor that looked like this, 10 to the negative 3rd power in M. That's essentially the same thing, just in a different format. Now after we've done that conversion, we can see that milliliters cancels. I plug in my given molar value, my 5 moles per liter, in order to have moles as my ending unit and in order to get rid of the liters that we were stuck with before. All of my units cancel except for the one I'm going for, so now I can calculate. This is easy as 25 times 1 times 5, all divided by 1,000 times 1, for a final answer of 0.125 moles. Notice that the question didn't even tell me a specific chemical. It doesn't matter in this case. I just know that I have 0.125 moles of whatever chemical it happens to be in this solution. Notice before that I didn't plug in the big M format into my calculation. I didn't plug in 5M down here. I converted that big M, the McDonald's sign, to moles per liter. I need to do that in order for it to actually cancel out my units in a dimensional analysis setup. So always make sure you're using this format, moles per liter or liter per moles. Now that you've seen me do it, go ahead and pause the video here and give it a try. Ready? Here we go. Hopefully you saw both ways that you could set this up. Either way, you'll get the right answer, 0.02 moles of NaCl. Go ahead and check yourself before you wreck yourself with these 2 test yourself questions, very identical and similar to the ones that were in today's lesson and examples. If you did them right, you should get an answer of 5.42 M or moles per liter for the first one. And if you got the answer of 0.097 moles of salt, for the second one, you also did it right. To recap today's lesson, we learned that molarity is the number of moles of solute per the number of liters of solution or solvent. In other words, moles divided by liters volume. And we were able to use that as a conversion factor to go from grams and milliliters to molarity, or to solve for moles of a certain molarity or concentration of solution with a certain amount of volume. Please give this video a quacks up and subscribe to my channel for some more quacky content.
No guts, no glory.